in that case, let's start. Um, the topic today is a thing called Cauchy sequences. Now, Cauchy sequences are quite important and they fill kind of a gap. So, let me give you a sequence. Let's see, how far can I go? Okay, there's a sequence. I think I got the numbers right. Does it converge? Assuming that the sequence goes on like you think it should, does that sequence converge?
Yeah.
Yeah. What does it converge to?
Hi.
Yeah. So this sequence converges to pi. Now, that's the right answer because in this course, unless said otherwise, we're always in the real numbers, okay? Now, let me ask you a different question. If I said we're in the rational numbers, does that sequence converge? No. Because you go think about your definition for convergence. In order to converge, you need something to converge to. Okay, so if you're in the rational numbers, pi isn't there. So you can't converge because there's nothing to converge to. Okay. So, on the one hand, back when we talked about the completeness of the real numbers, we said this is just the supremum property. Okay, every non-empty bounded set has a supremum, and we said that's the completeness of the real numbers. But on the other hand, this Cauchy sequences lets us capture another side of that coin, which is that in the real numbers, sequences which should converge do converge. Okay? This is a sequence that should converge, and it does. But over the rationals, because the rational numbers are not complete, this sequence, which should converge, does not converge. Okay? So that's where Cauchy sequences fit in. They're another side of completeness. Okay, I realize I haven't given you the definition yet, but they're going to be another side of the completeness of the real numbers. Okay, here's the definition. Oh, there's one more great thing about the definition of Cauchy sequences. It doesn't, I mean, in this course, in this semester, we're going to do it all in terms of real numbers, but the definition doesn't need to be in terms of real numbers at all. Okay. All you need to do the definition is a notion of distance. Okay, that's it. Okay, so the sequence xn is Cauchy if for every epsilon there is some natural number. I'm going to follow the book and call it h for now, such that for okay, let me do it slightly differently, such that the distance between xm and xn is less than epsilon for all indices m and n that are at least h. Okay, so we haven't proved anything yet. but this is going to relate to convergence. I might as well spill the beans. We're going to prove that being Cauchy is the same thing as converging if you're in the reals. Our definition of convergence is that you get close to something, and that something is your limit. Our definition of Cauchy is that the terms get close together. They get close to each other. Okay? And like I said, this is just foreshadowing for next semester, but all you need to make this definition work is a notion of distance. Okay? So this definition, you think about it, it works for the complex numbers, it works for R2, R3, R to the n more generally. It works for any space where you have a notion of distance. Okay. So, the big picture definition of Cauchy is that the terms are getting close together. Okay? That's what you should remember. And then what does that mean? Someone tells you how close they want the terms to be, and you can find a natural number such that after that point, they're all that close together. Okay? Every pair of terms after that natural number are that close together. Questions with the definition?
So, M and N can be arbitrarily far apart?
Yeah.
Okay.
Yeah. They just have to be at least H.
Thank you.
Let's do an example. The sequence 1 over n is Cauchy. Okay. Proof. Just like convergence, if we want to prove something is Cauchy, we start with an arbitrary epsilon. Okay, let me leave a blank and skip down to the computation part, okay? What are we going to want to do? We're going to want to compare 1 over m to 1 over n. Right? That's the distance calculation that's going to come into play, and we're going to want that to be less than epsilon. Well, what are we going to do when we get there? We're going to use a triangle inequality. That's at most the sum of both of them, right? Let's say I could make both of them at most 1 over 2 epsilon. And in fact, I'm going to want a strict inequality there, aren't I? Okay, that's our proof, except we skipped a little bit, okay? So how are we going to get this part, the important part there? 1 over m is smaller. Yeah.
Why are we doing 1 over 2 epsilon and not half epsilon?
Oh, because I'm an idiot.
Oh, okay.
There we go. Because I'm an idiot. Okay. Choose H. Okay, so 1 over m and 1 over n, let's see, m and n are at least H. So their reciprocals are at most 1 over H. So I want to choose H so that 1 over H is less than epsilon over 2, i.e. H is greater than 2 over epsilon. Okay? By the Archimedean principle, there's some natural number that does that. All right? Then, for all m and n, at least h, we have, and the computation that we did. Okay? Really, we could have written it all except leaving this blank until later, and just come back and filled in that blank. Okay, it's just like your standard definition of convergence. You leave a blank, choose capital N, so that, and then blank. You go on, you do the computation, you see what you need, and you go back and fill it in. Okay.
I have one question.
Mm-hmm.
So we're adding in, from our computation, we have an extra line in here that would say, like, after the 1 over m plus 1 over n, you'd have less than equal 1 over h, 1 over h. Okay.
Good point. Yeah, we should probably add that. Yep. I mean, yeah, it's fine if you don't have it, but yeah, to be crystal clear, I should have added that. Any questions? Okay. We've got the big theorem coming up. But before we get there, we should say, what does it mean to not be Cauchy? Okay. So we have to negate this statement. The statement is, for every epsilon, there's some h. Okay? So the negation is going to be, there is some epsilon for which there is no h, such that this is true. Okay? There is some epsilon for which there is no h, such that this is true. Another way to put that, if we drill down one more time, we're really just kind of removing the negation inside this parenthesized quantifiers. For every, there is some epsilon, such that for every h, there is some choice of m and n that fail this inequality. Okay? Let me write that down here. So, not Cauchy. There is some epsilon such that for every h in n, there are some indices m and n, at least h, such that the inequality fails. So you want to prove something's not Cauchy? You pick the epsilon, and you have to show that no h would work.
I don't mean to be nitpicky, but couldn't that technically be a greater than or equal to symbol?
That's not nitpicky. That's great. Yep. I'm sorry. I just saw Madeline's comment in the chat. Do you have to cite the Archimedean principle every time you pick the numbers? No, you never have to cite the Archimedean principle, as far as I'm concerned. I'm just going to keep saying it every once in a while. But you'll notice I say it, I don't write it down. Okay? And it's never the answer to anything on that quiz or homework. Okay? Just keep that in mind. Okay, this is how you show something is not Cauchy. So let's take a sequence. I've revealed our big theorem is going to be that Cauchy is the same as convergence. So if we take a sequence that doesn't converge, it should not be Cauchy. Okay, example. How about minus 1 to the n is not Cauchy. Let's just check that we can do this. Set epsilon. We get to pick the epsilon, remember. Set it equal to, and these terms are going to be, okay, so we should do this before we even write anything. The big picture, why is this sequence not Cauchy? Because the terms are not getting close together. Okay? The terms go 1, minus 1, 1, minus 1, 1, minus 1. That's not getting close together. That's why it's not Cauchy. Okay? So just, I hope it's obvious that it's not Cauchy. Okay? If this came up on a homework or a quiz, you could just say, obviously the sequence is not Cauchy. Okay? The reason we're doing this example right now, and the reason we're going to write it out, is just to get a little bit of practice with using the negation of the definition of Cauchy. Okay? But again, it's obviously not Cauchy. So, in the long run, successive terms are 2 apart. So, I'm going to set epsilon to be 1. Okay? Now, what do I need to show? I need to show for every h something happens, so I'm going to take an arbitrary h. Okay? Now, there are some indices. We get to pick those indices now. Okay? Let m be greater than or equal to h. So, it would be up to me to pick m right here, but that's all I need from it. Okay. And what do I want to compare it to? I want to compare it to the next term. Okay, and now I look at the distance between successive terms. That's the distance between, sorry, I don't have to look at the distance between successive terms. I look at the distance between xm and xn, but in this case, they were successive terms. Okay. How do I simplify this? Well, this is minus 1 to the m plus minus 1 to the m. Okay, I brought 1 minus 1 out. That's 2. And that is greater than epsilon. Okay. So, we picked the epsilon. Then we had to argue about any h, but then we got to pick the indices again. If you're proving that something is Cauchy, all of those are reversed. You have to argue about all epsilon, but you get to pick the h. But then you have to argue about all choices of indices. Okay? That's probably all the examples we're going to get to do today, because we have the big theorem.
Before we continue, I have one question about what it means to not be a Cauchy sequence.
Mm-hmm.
So, by being not Cauchy, does that mean that there's some distance at which no terms are ever closer than that amount? Like, in essence, is that what it means?
Right. So be careful. You've messed up the quantifiers in that negation.
Oh, I only need one to break it.
Yeah.
Okay.
Yeah. Good. That's a good way to say it. You're breaking, when you're not being Cauchy, you're breaking A for all.
Okay.
So you just need to find one pair.
Okay.
But you need to find that one pair for every H.
Okay. Okay.
Yeah. Again, I think I think everything is easier if you go up a little bit higher level and you say, okay, Cauchy means the terms get close together. How do I show the terms aren't getting close together? Well, I show that no matter how far out I go, here's two terms that aren't close together. Right? That's what you show. Okay. Any other questions before we go on to our big theorem?
So you have to prove for every H because if there's just one H, who's to say that the tail wouldn't exhibit that behavior? Or
Exactly.
what's that?
Exactly.
Okay.
Being Cauchy is only about the tails. So when you prove not Cauchy, you need to show that no tail does it.
Okay. So that's okay. So
Yeah.
that's why the quantifier is for all H, but you just only have to find one M N. Is that how it works?
Yeah, but they're going to need to depend on H.
Yeah. Okay.
Because if you just said, oh yeah, let M be 1,000 and N be 2,000, well then somebody could just come along and pick H further out. They could say let H
Gotcha.
be 3,000. So M and N both are going to have to depend on H. Okay. So in the proof, it looks like you're only picking one pair M N, but in reality, you're always picking infinitely many pairs M N, because you have to be able to go out as far as you can, as far as needed. Okay. So again, big theorem, 25 minutes to go, is convergence and Cauchy are the same thing. The lemma on the way there is that, well, if you're Cauchy, then since we're going to prove you're convergent, one of the consequences of that will be that you're bounded. Okay, and that actually is, we're going to need that in the proof. So here's our lemma. Every Cauchy sequence is bounded. Proof. We've done a proof just like this. I can't remember which one it was. Oh, yeah, I can remember which one it was. It was the convergent sequences are bounded. So we're just going to write the same proof. So that proof was set epsilon equal 1. There's nothing magical but 1. Anything would work. Oh. Yeah, okay. I wanna start with my sequence. So let xn be Cauchy and set epsilon equal 1. Okay. This is just a weird little grammatical thing. This is standard practice. Instead of saying let xn be a Cauchy sequence, we usually just say let xn be Cauchy. Okay. There is some h in n, so now we're using the definition. So we got to pick the epsilon, and the definition gives us the h. So that for all m n at least h, xm minus xn is less than 1. Okay. In particular, I'm going to specialize this now. least h x n minus x h is less than 1. Okay. Everybody clear on what I did here? I actually flipped this thing and I set m equal to h. Okay. Now again, the high level picture. This is saying the distance between xn and xh is less than 1. So what does that mean? It means that the absolute value of xn is less than the absolute value of xh plus 1. Okay? You can use the triangle inequality to get there. It's the weird other side of the triangle inequality. Or at least I always think it's the weird other side of the triangle inequality that takes you there. But again, you know, big picture, here's xh. Here's xh minus 1. Here's xh plus 1. And we know xn is somewhere in there. Okay, so the farthest out it could be is xh plus 1. Okay. So now we've bounded all the elements of the tail, so therefore, this was, I want to add a quantifier in here. For all n at least h. Therefore, for every n at least 1, what's my bound on the absolute value of my term? So I've bounded the tails already. What do I
So
need?
you just take the max of all the values up to the tail, and then the max includes h, so to speak.
Mm-hmm. Perfect. I'm going to go up to xh minus 1, I guess. And then I'm going to do an xh plus 1. That's the end of the proof. Questions?
This is like the proof when we showed every converted sequence is bounded. If it's past h already, then it fits the condition. If it's not, then you just take the maximum of every element before that, so that you're imposing like a bound onto every term of the sequence.
Yeah, perfect. Yeah, it's exactly like that proof. As it should be, because we're about to prove that Cauchy is the same as convergence. So, okay.
Excuse me, couldn't we also just say that, the first h minus 1 terms are finite, and every finite set is bounded, and the union of any two finite sets is bounded? Or is that's a little wishy-washy, isn't it?
That sounds a little bit more long-winded than what I wrote. Finite sets are bounded because they have maximums. So, as far as I'm concerned, that's the most important 3 letters in this proof. Okay, there's a maximum that we can take.
Okay, thank you.
But I'm not saying your approach is wrong. It's morally right, and if you get the details right, I think it would be fine. Okay, here's your theorem for today. We're going to prove this, and that's going to be it. We have 18 minutes to do this. I'm going to add an in R. That's a little bit inelegant. Let me do it this way. The real sequence is Cauchy if and only if it is convergent. Okay? We've already talked about this, but real is the key word here. This is not true over the rationals. Okay. It's not true it's not true if the only limits I allow are the rationals. Okay. Oh, I started with the example of pi. We didn't even go back to say it's Cauchy. I hope it's clear that it's Cauchy because I was doing the decimal expansion, so terms are getting close together. Okay, because their differences are bounded by the next decimal that I have to pick. Okay. Proof, it's an if and only if. The easier direction is that if you're convergent, then you're Cauchy. Okay? So, first, suppose xn converges to x. Okay, so now I have to take the definition of convergence and convert it into the definition of Cauchy. Convergence, again, high-level picture, this should work, right? Convergence means all the terms get close to the limit. Cauchy means every pair of terms gets close to each other. Okay? Well, if you're both close to the limit, then you're close to each other. Okay? Now, how close to each other do we want to get? In the definition of Cauchy, we want to get within epsilon of each other. So how close to the limit do I want them to be? I want them to be within epsilon over 2 of the limit, and then they'll be within epsilon of each other. Okay? So 15 minutes to finish this proof. I'm just going to write that down. Let epsilon be given. We know there is an n in capital N such that, again, I want the terms to be within epsilon over 2. Oops. Okay, therefore, for all pairs, we have, okay, now there's this little piece of algebra. Whenever we're using the logic that two things are close to something in common, therefore they're close to each other. Okay? It's an obvious true statement, but when we translate it into math, we need to add and subtract the common point we're comparing to, and use a triangle inequality. Okay. So this thing, we've done this maybe a half dozen times already in this course. And we add and subtract an h at the same time. Okay, now triangle inequality that. And that's what we wanted. Okay.
How was that adding and subtracting at the same time?
It's a little bit subtle, but you get this negative out here. So I'm subtracting an x, and then I'm actually adding an x. Because I've got a double negative. Did that clear it up?
Yes, thank you.
Okay. Anybody else? Okay. Notice in this direction, so what did we prove? We proved if you're convergent, then you're Cauchy. We did not use the fact that it's a sequence of real numbers. We did not use the fact that we're in the reals. This is a true fact, no matter what context you're in. All convergent sequences are always Cauchy. Okay? By the very simple logic that convergence means you're getting close to something, and therefore any two terms are getting close to each other. Any pair of terms are getting close to each other. For the other direction, we do have to use the fact that we're a real sequence, because we know the other direction won't hold for the rationals. Okay, so now suppose that xn is Cauchy. So by the lemma, it's bounded. Okay. Anyone know any theorems about bounded real sequences?
We have the monotone bounded theorem that we shouldn't call a theorem.
Yeah, bounded monotone sequences converge, sure. We get a better theorem than that, though.
The supremum property?
Yeah, it's not a theorem about sequences. What was our big theorem from Friday?
Is it the one about the subsequences? That there is a monotone subsequence in there? Maybe?
You're close. That was our penultimate theorem from Friday. What was our big end of the lecture theorem from Friday? Yes, Madeline has it in the chat. It's the Bolzano-Weierstrass theorem. Okay. You get a bounded real sequence. It has a convergent subsequence. Okay. Let's use it. This is why we had to prove that we were bounded. Therefore, by Bolzano-Weierstrass, xn has a convergent subsequence. So let's suppose the subsequence x and k converges to x is fine. Okay. So we started with a Cauchy sequence. Our lemma said it was bounded. So we got to use Bolzano-Weierstrass. So it has a convergent subsequence. Okay. We can't say that the sequence itself is convergent yet, but it has a convergent subsequence, and then the very definition of Cauchy says that every pair of terms gets close. Well, so they're all getting close to each other. In particular, all the terms are getting close to that convergent subsequence. And therefore, since the convergent subsequence is converging, and they're getting close to that convergent subsequence, they got to converge too. Okay, now we've just got to translate that into math. Okay? So what did we say? We said the terms are getting close to each other. Okay? And again, where are we? We're trying to prove that the sequence converges, right? So just like any proof of convergence, let's let epsilon be given. Okay, now we're going to use Cauchy. I'm just writing down the definition of Cauchy. But let's think ahead. At the end of this proof, we're going to say my arbitrary term is close to a term in the subsequence, which is close itself to the limit. So we're going to end up in the same triangle inequality logic as before. So I want my terms to be within epsilon over 2 of each other. So that at the end, I'm going to get within epsilon. Okay, this is true for all m and n, which are at least h. Okay. If we wanted to be a little bit more, if we wanted to explain a little bit better, we would say this is because the sequence is Cauchy. Okay. Now, what else do we have going on? The subsequence is converging to x. So there is also some capital K, such that the subsequence is within epsilon over 2 of its limit x. Okay, where are we again? We are trying to prove convergence. So I want every term of our sequence to be within epsilon of x. So how far out do I want to go? Any suggestions?
The max of K and H.
Yeah, that's what I was thinking, and then I just had a little bit of doubt. Let's skip down to the calculation, okay? We got 3 minutes. Should be plenty of time to finish this theorem. What are we going to do at the end of the day? We're going to want to compare our nth term to x, right? We know that what we're really going to want to do is, that means we're going to want to compare it to x n sub k. here, but we're gonna have to do that. Okay, that math works out, right? And then we're gonna say that's less than or equal to epsilon over 2 plus epsilon over 2 equals epsilon. We're gonna say it's less than this. Okay. Big hole in the middle here, but this is how the proof has to end. Okay. We are comparing, here's x, here's x sub n sub k, and here's x sub n. Okay. My variable choice is unfortunate, but with only 2 minutes to go, I'm not going to change it. I think it's a little bit unfortunate that I'm using an n and an n sub k. There's nothing mathematically wrong about that, but it's just a little unfortunate. Okay, so what do we need to put in here?
We need n and n sub k to be bigger than k and h.
Right. So here we need n sub. Oh, sorry. Here we need k to be at least capital K. Here we need both n and n sub k to be at least capital H. So what do we really need? We really just need this thing. Right? If I suppose n is at least h, then look at what I wrote here about the n sub k. I wrote that we need n sub k at least h and k to be at least h. It's little k to be at least k. Oh, so what I should really say, sorry, I realize I ran over a little bit. Well, let's just finish what we need to put in here. There is some n sub k with n sub k at least h and k at least h. So really we just need n to be at least h.
So what about capital K?
I forgot. I wrote an H where I meant to write a capital K in here. Okay. Come on, eraser. There we go. Okay, so I made a little bit of a mess at the end of that proof because I got a little bit lost. And the reason I got a little bit lost was because I wasn't thinking about the picture. Okay. let's think about the picture and see how this would show us what we need to do to end that proof. Okay. We have some convergent subsequence. It doesn't have to all converge from the same side. That convergent subsequence is converging to x. Okay. We're also Cauchy. But importantly, what am I doing? I'm choosing a term of the convergent subsequence which is within epsilon over 2 of the target. Okay. We don't actually need this to hold for okay. So I'm choosing one term of this convergent subsequence that's within epsilon over 2, and then I'm letting, by the Cauchy condition, I'm letting my other point be over here, but within epsilon over 2. And so, in total, my point is within epsilon of the limit x. See some
xn is within epsilon over 2 of, in that picture, xn4 or of x?
In this picture, it would be xn4. I'm saying that I want this to be less than
Okay.
epsilon over 2, and this.
Okay, thank you.
Okay.
We want to be within epsilon over 2 of something within epsilon over 2 of x.
Yeah.
Okay.
Yeah. So the end of this proof definitely is worth some consideration. Let me since we're 5 minutes over, I'm going to end our lecture here.